Thank you all for joining. But as a first disclaimer, I should warn you that if you hope to come here to get a lot of detailed explanation on new and fancy artificial intelligence and time series techniques, that I have to disappoint you a bit. I did dabble in artificial intelligence my whole career, but I'm first and foremost a power system engineer. And my topic, as already introduced, is the electricity grid. That is my domain. That is the problem I'm dealing with. And for that, I use artificial intelligence. Artificial intelligence is a tool for me, a means, but not the target. So that means that most of my work, or most of my talk, will be about electricity grid and the application of AI in that. And so since I assume that most of you that have joined have more of an artificial intelligence, data science background, I'll start off with a brief introduction of specifically the low voltage distribution grid and the challenges we face there. And then in line with the topic of this series, I will then afterwards focus a bit on the typical time series data that we find in the low voltage grid, those challenges, and then give you an overview of a number of lines of works, a number of sub-problems with time series that we're working on specifically in the AI Flanders research project. So I'd like already now to thank not only AI Flanders, but also the colleagues from KU Leuven, the PhD students and professors that assist us at EnergyVille with this energy applied artificial intelligence work. I will give due credits in time. And I would also like to take, before I start, the opportunity to thank Fluvius, the Flemish distribution system operator. Fluvius is not a member or a partner within AI Flanders, but they are so kind to make data available for us. And as you probably all know, artificial intelligence without proper and good data is worth nothing. But first, let's start with the description of the low voltage distribution grid. The whole electricity system is fast, and low voltage grid is only a small part of it. And actually, the energy system, the electricity system is, if you look at it in Europe, is literally spanning Europe. It is one of the more formidable machines that mankind has built, and actually in size, it's only overclassed by the internet. So it holds lots of plants, consumers, lines, different voltages, and so on. What I will be focusing on today is what is the last mile of that electricity system, the low voltage distribution grid, the cables that bring 230 and 400 volts to the households, families, and small enterprises, not the industry, not the big plants. Now, the distribution grid, as with also the transmission grid, all the grids basically in the electricity systems, is a natural monopoly and therefore a natural regulated monopoly. They are exploited by distribution system operators, which are kept in check, so to say, by our energy regulators. And the reason for that is that the grid is not only a natural monopoly, it would make no sense to build two distribution grids, it would be too costly, but also because the electricity grid is very much a critical infrastructure. Literally, if there's no electricity, society fails. And proof of that is the fact that disaster movies and books on electrical failures, that's a whole subgenre on its own. Not only is it a critical infrastructure, it is also a key component in the energy transition, and I will get back to what that means in a minute and explain you why this is so big of a challenge. But before we delve into that, this is a picture of the distribution grid. Well, it's not. This is a grass meadow. But it's a very useful analogy, I believe, for non-power system engineers to get a bit of an idea of the size and the complexity of what we are dealing with. A grass meadow contains thousands and thousands of individual small tree-shaped systems, blades of grass, and that is the same with the distribution grid, with the low voltage distribution grid, the feeders as we call them, which are small tree-shaped systems of cables. And like with the grass meadow, there are no two blades that are identical, yet they are all alike. And we have the same in low voltage grid. A very high variability, the principles remain the same, but no two systems are identical. Now, where the analogy breaks is that if one or more of these blades of grass wither, no one will complain. If that happens in the electricity grid, you have angry people because the lights are out. A bit more technical to translate what these blades of grass are in your mind. Basically, our low voltage distribution system consists of a huge, really huge meshed network of cables, and the starting and the end points of those cables, they start either at a transformer, you know, the small brick buildings or small container-like buildings that you find everywhere, and they end up often at the street boxes, of which you see a couple of pictures down there, the small gray boxes that you also find everywhere. And from all these endpoints where the cable pop up out of the ground, this is then broken down by hand, manual switching, into a large set of small tree-shaped systems. And so typically the setup that you would find throughout Europe is for every medium to low voltage transformer, 4 or 6 feeders that depart, which each contains of anywhere between 1 to 10-ish pieces of cable. And then the medium number of connections per feeder would be around 30 connections, so 30 households, but this could be one, a bigger company, or it could quite easily also run up to 200, 300, lots of variability. That's on the micro level. If you zoom out, as already referred to, the scale is huge. You see on top of my slide a couple of key figures. Just to give you an idea, small Flanders alone is more than 80,000 kilometers of cable. So we have enough electricity cable in Flanders alone to go around the equator of the Earth more than twice. And the number of these small feeder systems in Flanders alone, there are 200,000, actually closer to 240,000 to be exact. With high variability, every feeder is unique and it's a nonlinear system. The behavior in those feeders is nonlinear. And that nonlinear behavior is driven by 2 streams of data. And this is where I will get a bit more into the data science and will be touching upon the data and where AI is working on. The first block of data is the grid topology, what I have been describing, what cables are there, how long are there, where are customers connected, etc. and so forth. And the second block of data that drives the behavior of the grids are the offtake and injection profiles of the connection, meaning our sole production, our consumption, because we switch on a dishwasher, for instance. If you give me the exact accurate grid topology and the exact representation or the exact time series, and this is where the time series get in, of all the offtake and injection profiles, I can calculate deterministically what happens in those feeders. But this is one of the big challenges for the low voltage grid, is that neither of those 2 types of data is complete nor accurate. The grid topology, many aspects are not known. It's riddled with data quality issues and mistakes. And when we get to the connection points, well, digital meters are being deployed throughout Europe. They are increasing, but as I will explain a bit later on, we will not on medium term, if ever, get to the point where we have measurements of every connection point. So we have only a limited set of data measurement points. So what's the state of the art today then? How do we operate that low voltage distribution grid? Brief summary is we don't. The current modus operandi is that what we do is we calculate for a specific cable what giving all the connected houses what the peak is, the ultimate peak that those houses can draw, and then we put the cable into the ground, which is a bit bigger, so that it can ride all those peaks and has sufficient and ample reserve capacity. And actually, this is a very good system, because once we have that cable in the ground, we can forget about it for a couple of decades, don't need to spend any operational cost. And it's also a very cheap system because of our historic consumption profiles. If, say, you have 100 kilowatts of connected capacity to a feeder, then typically you only need to provide a cable tank that can hold 20 to 30 kilowatts to provide those. So we have a very because of the natural spread of the loads, you actually need only a limited amount of capacity compared to the connected capacity. And this is where everything changes. 2 or 3 years ago, we were still talking about preparing for the problems that were heading our way. Well, today, all the problems are there. Anyone following the news, apologies by the way for the Dutch, this is only for the Dutch news, but any news anywhere, there's not a week, and this year actually barely a day, that the energy system is not in one way or the other in the news. At all policy levels, regional, federal, European Commission, there are pushes for electrical cars, more solar panels, active customers, you name it, heat pumps, everything is being pushed, and all those appliances are increasing very rapidly, and all of them, at least everything that has to do with us, the regular families, the end consumers, end up in this low voltage distribution grid. Meaning that what we have is, on the one hand, a very rapid increase of the consumption of the grid. Just to give you a bit of a ballpark idea of what we're talking to. If you take an average Flemish family and their traditional consumption, if that family changes their diesel car with an electrical car, their consumption on year basis doubles, their peak almost triples. If you add a heat pump to that, the yearly consumption actually triples. And then you have solar panels, which all nicely produce together or not together. And then on top of that, and this is not unimportant, we have the emergence of demand response. Demand response is when consumption on the grid adapts itself automatically in function of the availability of wind and sun production. So if there's a lot of wind or sun, consume more. If there's not a lot of wind or sun, produce less. This is already business as usual for the big industry, that it's done by all energy intensive installations virtually. But this is now trickling down into the low voltage grids, and it's pushed very actively by the European Commission. In Belgium, not so much to now, but there are already a couple of countries in Europe where this is getting more and more spread, and Belgium will rapidly follow, actually obliged by the European Commission. The end result is that on the one hand, we have bigger currents, both positive and negative, both offtake load and injection reversed currents. And on top of that, not only are the loads larger, there's also more synchronization, more concurrency. So relatively speaking, the peaks grow. And that means that if we stick to the old way of working, simply putting a bit more capacity than the peak into the ground, we're looking to a lot of extra aluminium in the ground, and the cost there can really become prohibitive. And so the question is, can we do something alternatively? Can we employ other techniques? And that's actually where our work at EnergyVille comes in. What we are doing is we take our traditional power system engineering and we combine it with artificial intelligence techniques with a specific purpose to overcome this problem of sparse and limited and incorrect data. By combining those two fields, what we achieve is a statistical view with uncertainty on the state of the low voltage grids, but it gives us a better view than without any calculations, and that allows us to more optimally use what cables are there, to optimally configure them, and also only to invest there and exactly there where it's needed. And ultimately, when you have all these smart appliances on the grid, give them the right information so that they can balance with respect to renewable production, yet within the margins and the constraints of the low voltage grid, so that the costs and the benefits are properly weighed against each other. Our work typically follows a three-step process. Garbage in is garbage out. That's something that we all know very well. And so the first block of functionality that we're working on is getting these 2 blocks of data, grid models, and then models of connections, the profiles of connections, forecasting the connections, to get that as good and as well as possible. Also use AI techniques, given the limited measurements that we have, to improve our knowledge of what is in the ground in the field. Based on that, we step to a power system engineering step, where we calculate voltages and currents, not exactly, but probabilistic, since we have quite a bit of unknowns. And eventually, based on that, we estimate what are the congestions, do optimizations for topology and settings and the infrastructure, etc., and so forth. Here you see already all the time series popping up, with the sole exception of the grid model, which is more of like, in terms of a database, would be a hierarchical database, but everything else, from the profiles up to voltages and currents, down to even congestion forecasts, all of those are time series. And so let's delve a bit down and check what time series mean for our field. And they're very crucial indeed. As said, they are everywhere. Basically, every electrical property that can be calculated or measured at a node is typically for us a time series, and typically a 15 minutes time-based time series. Why 50 minutes? 50 minutes because if we would have longer time stats, 4 hours a day, we no longer have the granularity and the data to get a good view on what happens in the grid. We cannot go below 50 minutes. Simply because that would be too much data and too costly. Even more so, 15 minutes data, collecting that for every and each digital meter would be already too costly indeed. Today, typically a digital meter only collects day values, not 50 minutes data. On top of that, and this is an important constraint and an important aspect for us in our work to take into account, there's privacy. The data we are working with is extremely privacy sensitive, in the sense that, for instance, the EIN, as it's called, that is the unique ID that identifies your connection to the electricity grid. If you would check your energy bill, your electricity bill, you would find that EIN number. That is even considered by the European Commission as personal data. So that means that we have to be very careful with it indeed. On top of that, if you want to collect quarter-hour data of a household individual, then it's such that according to GDPR, you can only do that giving explicit written consent of the user. There's a single and very important exception to that, and that is acknowledge that for the good and safe operation of the grid, that you don't need permission. But even given that exception, it does mean that every time a distribution system anywhere in Europe wants to collect quarter-hour data for whatever purpose, that the regulators or the energy regulators are really on top of that distribution system operator to check whether the collection of that data is justified and proportional. So that means that not only cost, but also because of privacy, limiting as much as possible the amount of individual measurements that we collect is important. Let's then dive a bit into the properties of offtake and injection profiles, because those are some of the most important and interesting and challenging time series that we are confronted with indeed. You see an example of top with a zoom out. So this is for a full year and then a couple of days zoomed out from it. And what you immediately see, and this is very typical, and this is always the case, is that it's very volatile, jumping between, let's call it low level, almost noise, and then from time to time, very high peaks. So very unbalanced data indeed. And it seems pretty random at first sight, which makes sense because what you're looking at is real human behavior. One day I cook at 7 in the evening, the other perhaps at 6, depending on traffic. So we have all the regular human behavior stochasticity, yet there is still a bit of periodicity. To make it tangible, for instance, and I'll actually switch to the next slide because this is a good example. What you see here is typical time series consumption of one household with the squares each time the same time period of a day. So these are different days. And what you see is that you have this one peak that typically pops up in the evening. And probably this is like my habit is to switch on this dishwasher each time after I have eaten. It shifts a bit. It's a bit higher or lower, but it's mostly not always there. So there are a couple of statistical properties that we can work with, that we can use to forecast the chance, the probability that such a peak will happen. On to stress, it is the peaks that we are interested in. When you look at it from the perspective of the grid, all the low level, low consumption rumble down at the bottom, that doesn't matter. That is not going to do anything to the grid, no problem there. It is knowing when the peaks have a high chance of falling and how high those peaks are that is crucial for us to make an accurate estimate of the effective load and the chance that there will be congestions in the grid. Okay, what is our state of the art regarding this now?
Koen,
and what are we working on?
To interrupt you,
yes.
There's a question from Oliver that you might want to answer now, because it's about.
Okay, I'll check.
If you want, I can read it to you as well.
Yes, I'm checking it. Question is, more granular than 50 minutes would be too much data in terms of data storage. Actually, mostly in terms of data collection. So we have digital meters everywhere spread throughout Europe. Some countries already full coverage, some be in the midst of a rollout. And actually, in the whole chain of installing a digital meter, having the meter measure, and then sending data on and storing data, the most expensive component in the whole chain is getting the data out of the meter and reliably. And again, reliably is very important here, because this is the data that will be used to send you your electricity bill. We don't want any errors in that. And so reliably sending that data to the backend and to the database systems. In the SLA agreements for digital meters, this is really costly. So the more data you want to have accurately send over every day, that is really a cost factor. And cost is very important there. There's big push from regulators, from policy keepers, to keep the cost of digital meter as low as possible. And so limiting the SLA to get only the data that's strictly necessary is a very important part in that. I think that is the question. I hope that answers that question. To continue. What's clear from my story, or should have been clear, or I have failed, is that being able to model non-measured connections is really important. The vast majority of the connections, we don't have measurements. We only have a bit of meta specs, meaning that we know what type of connection there is, what type of tariff there is at that connection, what is the air consumption, what is the peak, that kind of generic stats, whether there is PV or not. And how we do it today, our current state of the art to model those connections, and I'll get a bit into the work that we are working on to improve this. The current model is we have a sizable database of historically measured year profiles of various connections, a couple of thousands of them. These are clustered based on the meta specs that I already referred to, with a simple k-means algorithm, very, very straightforward. And what we do, if we have a model without a connection without measurements, then we check based on the meta specs, we assign it to a cluster, and then we sample from the profiles within that cluster. And we don't do that just randomly. We do that based on the two specifications, the two parameters, features that we know from our experience are most important, being the solar irradiation and the temperature. That is what we use, and it works pretty well. But it can be a lot. There are a couple of cases where it doesn't work and it could be a lot better. So we have quite a bit of work on trying to improve how we model these non-measured connections. And I'll get a bit now from now on, from now to the end of my presentation. I'll browse over different smaller lines of work within AI Flanders, that's done within AI Flanders, so mostly in cooperation with PhD students from the KU Leuven, where we work on sub-problems regarding time series, more specifically and mostly regarding these consumption profiles. And so the first we work on is this, the clustering of profiles. Now this is mainly done with this k-means on meta specs. Basically, it's an ad hoc clustering using the domain knowledge that we have, and we're trying to improve this. So one line of work, and by the way, I always put the credentials on the slide for the work. If you are interested in this work, you want to learn more, if you know the people, by all means, contact me directly. If not, I will show my email address at the end of my presentation, and don't hesitate to contact me. I will be happy to play middleman and bring you into contact with the people that are working on these various research lines. So clustering. If we break that down, what do we need? Well, first of all, we need to define our clusters. We need to have a distance that measures whether two profiles are alike enough to be in the same cluster. And alike enough, again, recall from our perspective, from the grid perspective, means that two profiles are alike if the peak consumption falls within, has the same pattern and falls at the same, more or less the same time, and the peaks are more or less of the same size. What we've seen is that all the traditional distance measures fail to measure exactly that. So that's one line of work. And then the second line of work is, if we have a distance metric, how do we assign profiles using meta specs to different clusters? How do we make the link? The work on a profile distance. There is none in the literature, so we are working on devising our own dissimilarity measures. And we have at this point two candidates that we're in the process of validating. The first is our first attempt is based on DTW distance to measure the difference between individual days. And then what we are doing is for 2-year series of data, look within the year for days that match each other as well as possible using DTW, and based on all those possible permutations, come up with a distance value. First attempt, not perfect. It has some strengths, it has some weaknesses. We're still holding on to it because it does hold promise, but because it has some weaknesses, we've also tried to find alternatives. And the most promising alternative at this point where we're looking at is to use the Wasserstein-based distance metric. It's something I'm very enthusiastic about, holds a lot of promise here. And basically what we do there is, for a profile, for every time step, every 50 minutes or every hour of whatever resolution we choose to use, we calculate the distribution of the consumption values within that time step, as is visualized there. And so what we get is 2 series of distributions of the consumption values, and then using the Wasserstein distance, we calculate the distance between those 2 profiles. It holds a lot of promise. It's much more performance in computational complexity than the matching dissimilarity measure. It also has a couple of nice distance features. So I think that is a very good candidate of solving our problem, but we are, as we speak, validating this and see how it all performs. Then for clustering the profiles, which is the second task, and what we're doing there, and this is actually also a procedure that we use to validate the distance metric, is we use a combination of using our distance metrics, and we use a combination of expert-based clustering. our procedure that we use is using whatever distance metric we want to evaluate, we do a prior clustering of our profiles. Then we use the COBRA system, which is a system that can do clustering based on expert feedback to improve this clustering, meaning that the expert is presented one by one, each time 2 profiles, and we've built a shell around the COBRA system with a couple of specific visualization that allows an energy expert to make this evaluation of 2 profiles, whether they are alike or not. And the expert says, yes, indeed, they belong together, or no, these 2 should be separate. And the result of that corrective action then feeds back into the distance metric, and this is a bit of cycle that we're working right now in order to get to a good distance metric and a good clustering. Another line of work. As I referred, the behavior of the low voltage grid is very nonlinear indeed. That means that all the traditional algorithms to calculate currents and voltages, the traditional power system engineering algorithms, they are typically either optimizations or iterative algorithms. And we tend to use a lot of iterative algorithms, which means that they are computationally expensive. And if you want to calculate a full country scale, again, 100,000 of feeders, and you want to do that for longer periods of time, say a year, 365 times 96 quarter hours, then that becomes extremely expensive indeed. And so a lot of work goes into making this process, this type of calculations feasible, computationally feasible. One line of work, very interesting, is where we try to reduce the amount of days that we need to calculate to get a view on the load of a grid for a full year. And the task there is that given a set of profiles and year profiles, can we find out which days are alike in the sense that the consumption patterns during those days is alike, such that we can just take one representative day from that cluster and then from 20, 30, 40 representative days extrapolate for a full year. The current solution that we're investigating, it's plotted there. I will not go in detail through the whole flow. If you have any questions regarding that, please contact Kostas. I'm sure that he's very enthusiastic to explain more. But we have a solution there. We are evaluating it. And actually one of the very interesting side results almost from it is the following. Remember that when we sample today from historic profiles, we use temperature and solar irradiation as the most important features to select matching days. And temperature and solar radiation, that's something that's based on our domain knowledge, because we know it's very cold is typically when we get the highest consumptions. Now, by doing this day of year clustering, we actually also, by doing a feature analysis, we can also see which features are the most, indeed, the most relevant to this, that define the profile, the consumption during a specific day. And what gets out of that exercise is very interesting. We see on place 1 and 2, 2 solar irradiation parameters. So that's good, that confirms what we know. But then this third one, and that is surprising, is that instead of temperature, evaporation pops up. Meaning that, well, evaporation, the speed by which water evaporates, of course, is correlated to the temperature, but it is not exactly the same. And so this is a very important and interesting finding. It's one that that's high on our research agenda now to further explore and to see if indeed we use evaporation rather than temperature, whether our models and our forecasts become more accurate. Next. Up to now, we've been talking mainly about non-modeled connections, or non-measured connections rather. But as said, there is a share of connections that are measured, where we do have 15-minute values. And there you have the very very challenging problem that if we want to do any operational work, if we want to do anything to avoid any problems that are due tomorrow, then we need congestion forecasts. To forecast problems, to forecast congestions, that's an under voltages, over voltages, over currents, that kind of things, we need forecasts of the profiles. And so this is one specific, perhaps the most challenging line of work indeed, is that giving a measured profile where we have quarter-hour data till yesterday, and only till yesterday because digital meters typically only upload their data once per day. So given the data till yesterday, we need to forecast as good as possible the profiles of tomorrow. And for this, we've explored quite a lot of regression techniques, various types of neural network, extremely randomized trees, you name it. But all of these regression techniques, what pops out of this is always the same, and that is that they are good in getting the average behavior, and they're very bad in capturing the peaks. And as said, I don't care too much about the average consumption, I do care about the peaks. So they're exactly doing the opposite, or the opposite performance of what we really need. And so what we're currently exploring is to see how we can do this anomaly forecasting, because that is what it really is. It's not just simple regression, it's not anomaly detection, it's truly anomaly forecasting. So what we are now exploring is a number of alternative ways to look at this problem, and the most promising at this point is actually we try to reframe the problem. Rather than doing regression, we're looking into it as a classification problem. During this quarter hour tomorrow, will there be a peak or no, or not? Or if there's a peak, will there be a high peak, medium peak, or no peak? So make it a classification problem rather than a regression. And so that, as a basic idea, with a lot of other techniques that might be useful, is what we are exploring now in an attempt to solve this very tricky problem of anomaly forecasting. Let me check what's the time. Oh, okay, I have time. I'd like to round off with something that is, from an academic scientific point of view, perhaps, well, at least from artificial intelligence, less interesting, but I think it is a very fine example how standard, quote unquote, easy techniques, when properly used, can really make a big difference. One of the problems that we're dealing with, as I said, is the topology of the grid, that it contains quite a bit of errors, and that it contains and that there is quite a bit of stuff that we don't know. And one of the typical issues that we're confronted with is, on the one hand side, the assignment of houses to cables. So the data that we have, this house at that address is connected to this cable, that is often wrong. And next to that, a second problem is our grid consists of 3 phases. And you can think of it as 3 cables coming into the houses, and most, but not all, houses are connected to only one phase, to one of these cables. Some are connected to all 3. And when you have a monophase house, as we call it, we don't know to which phase they are connected. Should we know which houses are connected to what phase, then we have information to optimize how these houses are divided across the phases and actually make more use and better use of the assets of the cables that are already installed and in the ground. So this is a big problem. Correcting and correctly assigning houses to cables on the one hand side, and secondly, finding out which house is on what phase. And we can do that if we collect from digital meters, and this is a different type of time series, voltage data, so voltage measurements. And then the voltages of the 3 phases, they are internally correlated, and they have the same pattern over time. Not exactly, but enough to apply a standard classical k-means clustering algorithm on it. And what we've built is a whole pipeline that's based on simple k-means clustering, but it's enhanced with a lot of heuristics based on our domain knowledge. And we've built a pipeline that, given a set of voltage profiles, decides which meters, which connections are on what phase, and if there are any outliers, meaning houses that are actually connected to a different cable. We are starting the work to solve those questions and then in the end build this type of representative profile sets. Okay, and with that I am at the end of my talk.